Hi everyone, and welcome back to Educator.com. Today we're going to continue our study of fluids as we talk about the continuity equation. Our objectives are going to be to apply the continuity equation to fluids in motion, to explain the continuity equation in terms of conservation of mass flow rate. So, conservation of mass for fluid flow. When fluids move through a full pipe, the volume of fluid entering the pipe must be equal to the volume of fluid leaving the pipe. The law of conservation of mass for fluids. This holds true even if the diameter of the pipe changes. In short, what we call the volume flow rate remains constant throughout the pipe. And we'll look through a couple applications of that here. So, volume flow rate. The volume of fluid moving through the pipe can be quantified in terms of volume flow rate. The volume flow rate is the area of the pipe times the velocity of the fluid. And it must be constant throughout the pipe. So over here on the left-hand side, if we're looking at a pipe with a changing diameter, we have area 1 where the fluid has velocity 1. Over here on the right-hand side, we have area 2 and velocity 2. A1V1, the volume flow rate on the left-hand side, must be equal to A2V2, the volume flow rate on the right-hand side. What that means practically is that you must have a higher velocity or a faster flow over here and a slower flow over here. So let's look at some examples and applications. If water runs through a water main of cross-sectional area 0.4 square meters with the velocity of 6 meters per second, calculate the velocity of the water in the pipe when the pipe tapers down to a cross-sectional area of 0.3 meters squared. Well, continuity equation for fluid says A1V1 must equal A2V2. Therefore, velocity 2 at the skinnier section of pipe must be equal to A1 over A2 times V1, or 0.4 divided by 0.3 square meters times that 6 meters per second, or 8 meters per second. It gets a little narrower, it gets a little faster. Let's take a look at the garden hose example. Lots of folks have probably done this before. As you're watering the garden or playing with the hose, you want the water to come out a little bit faster, so you cover up the end of the nozzle with your thumb a little bit. You decrease that cross-sectional area so that the water has to come out faster to maintain that volume flow rate. In this problem, the water enters a typical garden hose of diameter 1.6 centimeters with a velocity of 3 meters per second. Calculate the exit velocity of water from the garden hose when a nozzle of diameter half a centimeter is attached to the end. Well, first, let's figure out what the cross-sectional areas are. When it's entering the pipe, A1 is pi R1 squared, or pi times, well, if our diameter is 1.6 centimeters, our radius must be 0.8 centimeters. So that's 0.008 square meters, or an area of about 2.01 times 10 to the minus 4 square meters. Area 2 at the nozzle is pi R2 squared, or pi times, well, its diameter is 0.5 centimeters, so its radius is half of that, 0.25 centimeters, 0.0025 meters squared, which is 1.96 times 10 to the minus 5 square meters. Now we can apply our continuity equation for fluids. A1 V1 equals A2 V2. This implies then that V2 equals A1 over A2 times V1, or 2.01 times 10 to the minus 4 square meters over 1.96 times 10 to the minus 5 square meters, all times V1, which was 3 meters per second, for a total of about 30.8 meters per second. Comes out a lot faster when you decrease that area. Let's take a look at an oil pipeline problem. Oil flows through a pipe of radius r with speed v. Some distance down the pipeline, the pipe narrows to half its original radius. What is the speed of the oil in the narrow region of the pipe? Well, A1 we'll call pi capital R squared. A2 is going to be pi times capital R over 2 squared, which is going to be pi times R squared over 4, or pi over 4 R squared. Now as we apply the continuity equation for fluids, A1V1 equals A2V2, which implies then that V2 equals A1 over A2 times V1. A1 is pi R squared. A2 is pi over 4 R squared times V1, which we'll just call V. We're going to have some simplifications. R squareds, pi, pi. We've got 1 over 4 times V, which is going to be equal to 4V. Gets 4 times faster. One last problem here. As we look at the roots of the continuity equation, which statement below best describes the continuity equation for fluids? Energy is conserved in a closed system. Mass is conserved in a closed system. Linear momentum is conserved in a closed system. Angular momentum is conserved in a closed system. Or charge is conserved in a closed system. Well, we're really talking about a mass conservation here. The volume flow rate is basically saying, the continuity equation is saying the mass that goes in must come out. Therefore, mass is conserved in a closed system. Hopefully this gets you a good start on the continuity equation for fluids. Thanks for watching and make it a great day.